welcome to the second part of your DC circuits tutorial. In our last tutorial, we used an analogy comparing the flow of electricity to a river. In this analogy, the current that we talk about when we talk about the flow of electricity was analogous to the current, the amount of water flowing past a certain point at a given point in time. There's our definition for current. Now we want to talk about what happens when that river heads over a waterfall. This is potential difference. Potential difference is defined as the change in the electrical potential energy per unit of charge, but that's not very helpful. The most helpful analogy to understand potential difference may be that of gravitational potential energy, our old friend PEG. We all understand that when water flows over a waterfall, it goes from an area of high potential energy to an area of low potential energy, and a circuit can be thought of in much the same way. Since we're only talking about DC circuits, which use direct current, it's helpful to think about a battery as a system of two cells where one has got a lot of charge carriers, in this case electrons, and the other really needs them. So they flow from the area where there are lots of them, the area of high concentration or high potential, to the area of low potential, just like water flows over a waterfall. The unit for the current is the amp, given by the abbreviation capital A. The unit for potential difference is the volt, given by the abbreviation capital V. As you might expect, when we look at a certain circuit, the amount of charge that can flow past a given point at any moment in time, otherwise known as the current, is controlled by the amount of potential difference across the cells of the battery in a direct circuit, and the amount of resistance that that charge faces to flow as it travels through the circuit. This relationship is given by the equation delta V, the change in potential, is equal to IR. In this equation, I represents current and R represents resistance. A fun and easy mnemonic to remember this equation is twinkle twinkle little star, V is equal to IR. So can we figure out how much current is flowing through the circuit shown here? Of course we can. Let's list our variables. Okay, so we've got a 6-volt potential difference across the circuit, and we've got one resistor with a resistance of 2.0 ohms. To find current, we simply rearrange this equation. So now we have voltage potential difference divided by resistance is equal to current flow. 6 volts divided by 2 ohms means that 3.0 amps is the current that's present across the circuit. So let's assume that we have a 24-volt power source on a direct current circuit, and wired into that circuit we have some sort of device which requires 15 amps of current be delivered to it for it to operate correctly. The question is, what size resistor do we need to wire into this circuit to make sure that the device receives the correct amount of current? Again, we turn to V is equal to IR. So we rearrange to get V over I equals R and take 24 volts divided by 15 amps to get a resistance of 1.6 ohms. We need a 1.6 ohm resistor wired into this circuit to ensure that the device in question gets the 15 amps it needs to operate properly. Not so hard, is it? Whoops. Make that a 1.6 ohm resistor. But what if we don't have a 1.6 ohm resistor? Aha! This is where knowledge of equivalent resistance comes in handy. So now, let's imagine that I have the same 24-volt power source, the same 24-volt battery, and the same device that needs 15.0 amps to operate, but all I have in my drawer are a 2 ohm, a 3 ohm, and a 4 ohm resistor. Is there any way that I can wire these resistors to get close to the 1.6 ohms that I need? It's important to note that if you're wiring resistors to get equivalent resistance and you can't land exactly on the 1.6 that's needed, you can have slightly higher resistance that will just deliver lower amperage to the device, less current. But if your resistance is too low, you'll deliver too much current to the device and it may blow up or burn out. Our first option, our first thought, might be to wire them all in series. And if we put the 2, the 3, and the 4 ohm resistors in series, we get an equivalent resistance of 9 ohms. That's way too high. The device in question won't get nearly enough current to operate. What if we wired them all in parallel? The 2, the 3, and the 4 ohm resistor wired in parallel yield an equivalent resistance of 1 over 2 plus 1 over 3 plus 1 over 4, or 1.05. When we take the reciprocal of 1.05, we get an equivalent resistance of 0.95 ohms. That's way too low. It'll deliver too much amperage to our device, and nothing good comes of that. Kaboom. Obviously, the solution to this problem is wiring our resistors in a combination of series and parallel. Your job? Figure out a wiring scheme for these 3 resistors that gets you as close as possible to 1.6 ohms without going under. Good luck!